All right, are we live? All right, hi everybody. Welcome again to another Rust meetup. Thank you so much. We have a great lineup of speakers out here to present today. But before we get into that, there are just a couple administrative things that I want to mention. First off, on Sunday, we are doing a Dockathon. It's going to, I believe, Brian, correct me if I'm wrong, it's going to happen here on Sunday at 12 p.m. Do we meet in this room or? Okay, we'll meet here at 12 p.m. And for all of you out there on the internet, we will have an IRC channel to participate, and we'll be working off of an Etherpad. We're going to meet up after the presentations. We'll just kind of form a small group and chat how exactly we want to find the docs that we want to document after this, and we'll talk about it over tomorrow and Saturday on the IRC channel and email, so everyone can participate. Also, for April, what I'm trying to organize is it's going to be a very test-friendly meetup, and also I want to pull together a testathon. Like we used to have a fuzzer and reducers, and I'd love to revive that. So anyone out there that's working on something test-related, please let me know, and maybe I'll be able to get you into our schedule. So on to our presentations. First, we'll have Julia presenting her amazing OS that she worked on without knowing anything about OSs or Rust. Patrick is talking about his great progress with the parallel layout and oh, sorry, that should be Servo, not Rust. And finally, Alex will close out the night to talk about his debugging work. So, on to Julia. Please give her a warm welcome.
Hello. So, thank you for organizing this. This is excellent. Normally I don't live here, so it's exciting to come out to a place where there are Rust meetups and I can talk about silly things that I did. I wonder if I can get this to work. Let's see. That looks reasonable.
No. What does
Yeah.
it say when you plug it in?
1024. Yeah, this is gonna work.
No. Why you weren't supposed to change it?
I didn't.
Okay. What does it say?
Everything's fine.
Okay.
Nothing is broken and everything is fine. Look straight ahead. Oh, I can see the screen there. Look at that. Sorry about the lack of display issues. I'm gonna fix this for you all, and then everything will be fine. Okay. So I want to talk about how I wrote an operating system in Rust. And when I did this, I didn't really know any Rust, so I started learning Rust. I think I spent a whole day on it, on learning Rust before doing this. And I also didn't really know anything about operating systems at the time. So what happened is I was at Hacker School. And Hacker School is this 3-month program where you can do anything you want, right? So when you have that opportunity to spend 3 months doing anything you want to become better at programming, I thought the natural choice was to do things I was most scared of, right? So I was like, operating systems. What is it? How do I do it? Because I did a computer science degree, but I avoided all of the classes where you do things like programming and operating systems, so I didn't know, right? I was like, so I'd spend a while kind of mucking around with the Linux kernel at the beginning of Hacker School, and at the end of Hacker School, I was like, okay, things are serious. It's almost over. I need to write an operating system, like stat. So Lindsay Cooper, who did some work on Rust, was at Hacker School at the time, and she was like. And I was like, I want to use Rust for something, but I'm not doing any systems programming. Also, I want to write an operating system starting today. And she was like, do you realize that your statements are contradictory, and maybe you should write your operating system in Rust? And I was like, okay, cool. So I started. This is my operating system is called Puddle, because it's really fun, but then also you get wet, and it's sort of a bad idea. And a lot of things went wrong along the way. Okay, so the first and most important step is to copy some code from the internet, right? There's this thing called rustboot, It's a little tiny kernel written in Rust, and it looks like this, right? You start it, and it turns the screen red, and it hangs, and that's it. That's all it does. This is amazing, right? Like, this is a huge advance over what I could already do, which was nothing, right? So I had this, and I was like, sweet, this is cool. So step 2 was to be like, well, if it paints the screen red, maybe I can paint the screen blue. I promise I did more than this. This is like a surprisingly important step, right? Because like it's like I actually had to go look at the code and be like, this isn't totally terrifying. And in particular, you can see here that it says like clear screen light red, so I changed that to blue, right? There's this enum up here which is like, and I was like, okay, I can build it, I can run it in my emulator, I can change something, I can program. This isn't a total loss, right? So, the next thing I want to talk about is like, why can you write an operating system in Rust, right? Like, what does it mean that you can write an operating system in Rust? Because this is something that was really unclear to me, and maybe clear to all of you. Like, in what languages you can write an operating system. So you can't really write an operating system in Python. Do people know? And this might seem obvious, right? Because like, you're like, Python is kind of a high-level language, and kernel is kind of a low-level thing, right? But like, there are like concrete reasons why you can't write a kernel in Python. Like, let's say with CPython, right? So there's a CPython interpreter, right? Which ultimately is like compiled to like write like a binary, right? Which you could conceivably just like have and run somehow. But when you run CPython, right? Or like when you run any normal program that's on your computer, like when it does things, like let's say like print to the screen, it does that through your kernel, right? Like there are system calls, and the system calls go through your kernel, and you can't write a kernel on top of a kernel because you don't have a kernel, right? Which is like sort of obvious if you know about kernel programming, but if you don't, you're like, oh yeah. So this is like huge moment of enlightenment for me, where I was like, if I don't have a kernel, whoa. Like, I don't know, it kind of blew my mind, right? And if you try to do things like, if you're writing in C and you try to use like standard library things, right? And if you do like include standard IO, printf, suddenly it's like, wait, what is printf? Printf calls like the right system call, but there are no system calls. Oh no, right? So you kind of have like the rug pulled out from under you, and you can't, like, you have nothing anymore, right? But you can write a kernel in Rust, which is kind of abnormal, right? If you think about it, you're like, oh, wait, why can't I do that? Doesn't Rust use things that might require using system calls? But you can say, Rust, take away all the things, right? And I think this is called running Rust in like freestanding mode. One of the things in my kernel is it says like no std here. That means like, I've got this. I don't need any stupid kernel. I'm doing like, I'm in charge. I get to do everything, which is fun. But it also means that you lose a lot, right? Which is a bit terrifying. So let's talk a bit about like when you're writing a kernel, the things that you don't have. So you have some hardware underneath you, right? You do not have, like, you can't allocate memory without writing your own malloc function, right? One thing that really surprised me that I didn't think about was you don't have like a sleep function. Like if you want to like wait, like what I ended up doing was I wrote these like for loops which would just like iterate 80 million times to like use up cycles so that it would take time, because I was like, there's no sleep. That's not a thing. I would need to do that myself. I see how it is, right? Like there's no processes, there's no drivers. Like you can't like type on your keyboard and have it work, because that would mean that you have a keyboard driver which you don't have yet, because the only thing you have is a screen that's red, right? Like that's it. Like you don't have a file system like at all, right? Like you would also need like an IDE driver or something for your hard drive, like, and then you would need a file system on top of it. Like that's like a whole can of worms. There are no processes, there's no like separation of privileges between different processes, even if you did have processes, right? Like everything is all in the same place. Anyway, so you've lost everything. It's kind of like you're like a little child, and you don't have anything like except like some assembly, and like you're like, okay, what do I do? So I was like, what do I do? maybe I can write some text to the screen, right? Like, this is what we do. We write hello world. And this seemed approachable. This was kind of approachable. So you can see, you may not be able to see, but it's basically what you do is there's the address of the VGA buffer, which if you go up here is like B8000. So that's fine, right? Like there's this thing, and every character is 2 bytes, so you just need to figure out what the right bytes are and put them in the right place. And that's kind of like indexing into an array, right? This is something that we can kind of do if we know C. So like from a operating system's perspective, this was totally fine, and from a Rust perspective, this was like a total disaster, because like I would try to do things. I would be like, oh, I want to convert my string to an array of bytes so that I can iterate over it, or like I want to iterate over a string. And like this, like I want to iterate over a string was like this like really long conversation in IRC where like I had like a lot of discussions with people in the Rust IRC channel over like how do I do this? Because in normal Rust it would be fine, and there are like methods and stuff that you could call. You could just be like str.asBytes. But instead I was like, and I'm using freestanding Rust and I don't know Rust. Sweet. But the person who writes so because you've lost your standard library, right? Like you took it out, so now you can no longer iterate because your standard library is gone. So that's kind of terrible. So there's this library called Rust Core that gives you your standard library back, which is fine, and it would probably be more fine if I actually knew Rust. So basically the people in the IRC channel were like fantastically helpful and like answered all of my questions within like a second. I'd be like, I am having a problem, and they'd be like, yes, we're on it. And I'd be like, but I have more problems, and they'd be like, yes. And like, it was an amazing experience, right? And this code in the end looks kind of simple. It's like let bytes equals thing for b in iterate over bytes. That took me like an hour to write, or like more. I don't know. It was extremely confusing, and I needed a lot of help. But people were very helpful, and then I did it, and it was fine. And then the result of that was that I could print stuff to my screen that was red, right? And I could like have different background colors and foreground colors, and it was like super fancy, like the 80s or something. I don't know. So I was super happy. So the next thing I wanted to do was, I was like, well, if I can print to my screen, I would like to be able to type on my keyboard, right? Like these are like little tiny baby steps. And I was going to have a demo here, except my computer froze. The demo is really boring. Okay, like imagine a demo where I bring up an emulator, and then I press some keys on my keyboard, like A and J, and then those keys get displayed. Like, and it'll be like A, S, D, F, right? Like this is what I'm trying to imagine. I want you to imagine happening right now. That's it, guys. So this is where I was trying to go, right? And like this was like terrible. Like it was a disaster. It was so hard. So I want to kind of explain what was hard about it a little bit, and like some of the things I went through to make you try to feel like bad for me. But it was pretty fun. So what happened? This is a long list of things. So to get interrupts working, the idea is there's some kind of like interrupt handler piece of hardware in your computer. And when you press a key on your keyboard, there's an interrupt table, and it'll go like look up the appropriate entry in that table. Like it's like interrupt 1, right? So it'll go look up entry 1, and there'll be like an address of some code there, and it'll jump to that code, and it'll go run the code, and the code will be like, okay, I'm done, and then it'll be done, right? Which sounds simple in principle, right? And there's like, you need to do some like global descriptor table, and there's an interrupt descriptor table, and there's an instruction to load the interrupt descriptor table. So you would think that you would make this table, you'd load it, you'd like press keys, and then they would display, and your handlers would run. And this is like not the case. This is not how it worked for me. So the first thing is I like tried to make a table, and I tried to do it, and just like nothing worked. Like I would press keys and just nothing would happen. I'd be like, well, that didn't work. So then I would try other stuff, and I would press some keys, and nothing would happen. And I would press try more stuff, and I had like reference implementations. I had like some C code. Nothing worked. So at some point I realized that interrupts were turned off, and I needed to turn them on, right? So I turned interrupts on, and then it crashed, right? Like the whole thing would just crash every time I brushed the key, and I was like, sweet! Like this is a huge improvement. Now it does something. But like I got like less happy because I kept on trying things, and it just like continued to crash forever. And so then I discovered that there's this wiki called the OSDev wiki, which has a really useful article called "I Can't Get Interrupts Working." If you ever have this problem, go read that article. It's incredible. So it was like, okay, you're trying to do everything all at once. It was kind of like someone had read my mind, and like every time I had a problem, it was there, and it was like, I know. Like, I know what you're going through, and I have already foreseen all your problems. So it was like, first you should try to set up your table and then trigger the interrupts manually, because apparently you can trigger an interrupt manually. And I was like, yeah, good idea. Like trying to like do only one thing at a time so that your program is more likely to work. That sounds like programming, like good practices that I know. So I did that, and I was like, sweet. And then I set up my interrupt descriptor table so that it was not broken, and I could trigger an interrupt manually. And then I was like, okay. So I turned interrupts back on, and it still doesn't work. And I'm like, friends. So then I read the article again, and apparently the word for this is I'm receiving EXE9 instead of IRQ1 when striking a key. And what that means is apparently x86 just doesn't work. So like, you press a key and you expect to get interrupt 1, but instead what it does is it just crashes. Like, that's like the normal behavior. That's just how x86 works, apparently. So what you need to do is you need to remap the programmable interrupt controller so that interrupt 1 is actually mapped to interrupt 33 so that it doesn't crash, because it can't tell the difference between 1 and like, I should just explode now. And like, I don't know how this is like a thing, but that's like x86, I guess. Like, I think this is just what hardware people deal with all the time, but I didn't know. Like, maybe you're hardware people and you did know. But I had no idea, right? So then I do it. I like remap my PIC, and I'm like, okay, I'm awesome. It's going to work. And it didn't work. But this time it didn't work just because like I forgot that I remapped it, and I'd like left it at 1 instead of changing it to 33. But that took me like 2 days. As usual, right? And then it ran, and I was like, oh my god, I can get an interrupt handler to run. So at this point, it's like I can press a key, and it'll always print J. Right? Like, which is amazing, right? Like, I press a key and it does things, which is what I was looking for. And so that took like 6 days, right? And I was like, okay, now the next thing I have to do is I have to get it to like print the actual thing that I pressed. So that seems like it might not be too hard, right? Like, okay. So I wrote some code to do this. The code I wrote involves an array. So the way interrupts work, the way like keyboards work is the keyboard, the hardware will like tell you which scan code you pressed. So like on your keyboard it'll be like 1 2 3 4 5 6 7 8 9, right? So like 1 maps to Q or something. I don't know what the order is. It's like kind of like the order that it appears on your keyboard, like so graphically, except it's different in some like subtle ways that I don't understand. But I was like, I'll just make a big array that I'll copy from the internet somewhere, right? Which has all of the like ASCII characters that I want, and I'll just put like question marks for the things that aren't really printable, because I don't even care, right? Like, I just want to type words. I don't care if like I can press F1. I don't care about F1. And then I will like take the scan code and like index into my array, right? And I thought that this would work, and it didn't work. So that's kind of sucked. But what happened is I always got 0. Like every time I tried to index into my array, I got 0. And this was kind of scary because I was like, I thought I knew how to program. Like, why am I getting 0? This makes no sense, right? It made no sense. But I was like, I guess this must be for reasons. And I at some point discovered that if I like linked my program differently, then it would start working, and then it would work for a while, and then at some point I would compile it and it would stop working again. And then like maybe I linked it differently and then it would start working. So I was like, oh, I have some kind of linker problem, right? And it was, so I read like 10 articles about linkers. So there's this like really awesome like 20-part series about how linkers work. So I started reading it, and I was like, maybe I'll learn what my problem is if I just learn like everything I can about linkers, right? So it's been like a day of reading about linkers, and you don't have to read this blog post right now because it's like a million words, but I just want to kind of give you a sense of like all the things I wrote down. Like this is a summary of everything I learned about linkers, and it was a lot, and it didn't help at all. Like, at the end of it, I had no idea how to solve my problem still. I was like, I looked at it, I understood much better how like my binary was structured and how binary formats worked, because I have like this like ELF thing, and I could like look at it and I could find my string in my binary, and I was like, the array is there, I can see it with my eyes. But it doesn't work. Why doesn't it work? And I had like all these crazy ideas about why it might not work too, with like, I don't know, like position independent code. I don't know, because I read all this stuff about linkers and I was trying to apply my knowledge, right? But it didn't work, and like none of my knowledge was something I could apply. So someone in this blog post suggested that I use GDB, right? This was a good idea. So I was like, I'll use a debugger, right? He was like, you can do like remote debugging where you like attach your emulator to GDB and then you can like debug your operating system while it's running, which is amazing, right? I was like, that sounds like exactly what I want. So it took me like a long time to figure this out. It took me like probably a couple of days, and like I asked people, and anyway, but like no one could really help me, except the internet. So I blogged really loudly about all this stuff, right? And then people would in the comments tell me how to use QEMU with GDB, and I'd be like, I love you, you're my favorite, right? Like, because nobody, like, I just didn't know what to do. Okay, right, so I got GDB, right? And I was like, what? And then I found my array, and it was all zeros. Like, I found its address, and it was actually all zeros. And I was like, oh, I'm getting zeros because it's all, but why is it all zeros? And that was really sad. So I wrote a blog post, which called, and the blog post is called, "Something is erasing my program while it's running." Because that was like the only conclusion I could draw, right? I was like, I have a program, it's not all zeros when I start, and then I run it, and then it's all zeros after. Like, but it's like a gremlin that's erasing it. And it was terrible. So I posted this article and I tweeted it, and someone was like, hey Julia, is your binary larger than 12K? Because your loader is only loading 12K of your binary. So like, you remember how at the beginning I was like, step 1, copy some code. So step 2 was not read that code, right? So that was kind of like true. So that this is my commit, fixing the problem, right? You'll notice that there's a typo where I'm like, oh, I should load more of it. And it was less than 24K, so I was just like, I'll just load 24K. And like, it's weird, because like, the kind of problem that I'm used to having is not like I have a program and accidentally half of it got lopped off, but then it worked fine. Except for like, because there was other things in that part of the program. It wasn't just that array. And I don't really understand why it works still, right? Like, there was other stuff happening there. And you would think that having a loader that just like is like a guillotine would be a problem, or like a bigger problem, but apparently not. Apparently that's fine. Apparently that's what writing operating systems is like. So that was the worst thing that happened, but it was actually really good, right? Like, I mean, if you think about it like objectively and not from the point of like how sad I was, like I did read 12 articles about linkers, and that was like, they were really good articles, and I wasn't gonna read them if I wasn't upset because I thought I had a linker problem. And it was a good like debugging exercise. Though I told someone in an interview about this problem, and I was like, they were like, how'd you figure it out? And I was like, someone on Twitter told me. And they were like really not impressed. But like also I didn't really want to work for them. So that was okay. Because I thought it was pretty impressive that I got someone on Twitter to fix my problem over Twitter. Anyway, we can talk later about who was right. So we talked about everything we lost, right? Like we lost memory allocation, we lost sleep, we lost threading. So far the only thing we've gained back is a keyboard driver, right? Where we can type. So it's like maybe we could gain back another thing. Okay. So I assume that you know Rust. Probably better than me, right? Like let's be real. Because I was basically writing C code except writing it in Rust. Like I didn't actually allocate memory. I just like implemented memory allocation for kicks. And like I understand the whole point of Rust is like something to do with memory. So if you're not allocating memory in the first place, like what are you doing? Anyway, so there's this statement, right? Which is like allocate a 2 and put it on the heap, and like X is like a pointer to it, right? A node pointer. So I said that we don't have memory allocation, right? And then so this statement doesn't work. It won't compile if you don't have that, right? So how does that work? So it turns out that you can kind of like swap out Rust features, and you can say like, let's just get rid of all the features, and then you can bring them back. So this is a part of Rust core, which adds back some things to do with memory allocation, right? And it's like, well, I'll bring back like the exchange malloc. Where is this? Exchange malloc, right? And what this does is it requires that you have a malloc function, which is like written using the C ABI, application binary interface, because Rust functions and C functions are apparently different. Anyway, so if you have a malloc function somehow, this was like, okay, if you have a malloc, I will let you allocate memory, right? Like if you write me a malloc function, then we can do this, right? And then this statement can work if you, right, so it's like kind of like contract, right? And it's like if you implement the like appropriate like threading functions, then we can do things like the Rust threading things, right? So I was like, this is awesome. I'm going to implement malloc. So I did. I'm not going to go through it because it's really boring. It's also really bad. So in particular, like it was impossible to free memory because I was like, I'm not going to write a real malloc. I just want to do it for fun, and like I'm only doing it today anyway, right? And also like my kernel was under 24K, right? And I wasn't doing anything, and I have like 4 gigabytes of memory on my computer. I'm like, I'm definitely not going to need to free, right? Why would I want that? So I didn't implement 3. I only implemented malloc. But another thing you can do is you can implement a malloc function. Where do I have this? That always returns the same thing. Right? You can implement a malloc function that has a fixed address and just always returns that address. And this is amazing, because it means that you can write code like A equals something, right? B equals something, and like allocate a whole bunch of different things, and they're always going to be all the same, right? You can have like a million integers, and they're all the same damn address. Infinite, right? You can have an infinite number, and you always use the same amount of memory. This is a fantastic memory saving technique. And it like really worked, right? I was like A equals like 2, and like B equals like, or A equals A and B equals B, and I printed A and B, and they were the same, and they're always the same, and of course they're always the same. So there's nothing like intrinsic about like Rust that means that like your programs work. Like if your malloc function doesn't work, then it's over. So that was something cool that I learned. I never really thought about that before. That made me really happy. Oh yeah, and now I'm actually done, I think. Am I done? What time is it? How are we for time? Can I talk about something else? Of course. Yeah? I could talk about running programs. Running programs is really fun. It turns out that you can, this is something that's like feasible for you to do. So I tried to run a program. I got like halfway there, and then I stopped. In particular, I tried to run a program that didn't do anything, which is like surprisingly hard. So the way I ran a program, because like this is a sort of fun thing, right? But normally when you run programs, you think of it having them on a file system, and one of the many things that we don't have is a file system, right? So what I did was I just had like a little program that I embedded inside my kernel somewhere, and I just knew what address it was at, and I was like, okay, this is in memory somewhere, and I know where it is, and I'm gonna try to run it, right? And it turns out that doesn't just work. Like you can't just jump to the beginning and have it work, which is sad. I was hoping that I was just gonna be able to do that. But then what I learned is that binary formats are file formats, right? Like we know about like JSON or like what's another file format that we all understand? XML, yeah, like XML, right? Like it's text and you kind of know what it is. But when I thought about binaries, I was like, binaries are a magic format made of magic that I can't understand, right? And like binaries are this impenetrable thing. And it turns out that, I mean, obviously that's not true, but it turns out in real life it's not true. Like if you have like an ELF file, so ELF is like the binary format for Linux, which is all I know about, because I kind of like was like, I know about things on my computer and I have a Linux computer. There are some like magic bytes at the middle, and then there's like facts about the file. And there are utilities that help you read it. So there's a utility called like read ELF, which lets you look at it and like shows you all the different parts of it and all the different like sections and like segments. And in particular, you can figure out fairly easily where there's a part called start, and that's the part that you need to jump to. So basically all I need to do was like make an appropriate program, which I had no idea how to do, because normally when you compile a program, it has all kinds of stuff in it that like the GCC adds. So the only way I ever figured this out is that Graydon, who I understand is fairly important in this community, sent me an email because I wrote a really long blog post being like, I don't understand, and he was like, here's all the information that you might ever want. And I was like, I don't even know you, thank you. That's the best, and it was really nice. And he was very nice about it. And in particular, he gave me a program, which was very key, which was like very small and had almost nothing in it. And then you can actually take like a binary and like read, like look at like the bytes and like understand everything that it does. And that was a pretty big revelation for me. Anyway, so like this was a super cool project. I want to like thank people. So like I hung out in the Rust IRC channel a lot. These are just people who like mentioned me after I asked questions. Right? Like, can we do that again? Like, this is how much people helped me, right? Like, I'm sure some of you are here, in which case I want to thank you, because it was like I have no idea what I was doing, right? Like, it was a total disaster, and I also didn't know Rust. And the cool thing about writing an operating system in Rust is if you're writing an operating system in C, tons of people have done that before. So it's really hard to get help because you'll be like, I don't understand this thing about inline assembly. And if you go to like, there's no IRC channel that I know of, but I feel like if I went there, people would be like, maybe you're stupid or something, right? But in the Rust IRC channel, people were like, I would ask like really like beginner questions about strings in Rust because they're kind of confusing. But then I'd also just like sneak in operating systems questions, and people would just like answer those too, and everyone was super helpful, and I got all kinds of help that I don't know how I would have gotten otherwise. Yeah, and everyone was super friendly. Here are some of the people who helped me. They were like delightful. It was like not a possibility. Like this is like one of the first questions I asked. It apparently got answered in 0 seconds, right? Like I don't even understand. It was really good. And like I learned all kinds of stuff. Like I never took an operating systems class because I thought it was stupid. And then I was like, oh shit, I was wrong. Like, but I learned about like binary formats and linkers because apparently I read a million articles, and I learned about assembly and how like the root process works and like the difference between like protected mode and real mode and like interrupt handlers and how starting a program works, like kind of from scratch, like the whole thing, and malloc, and it was like kind of like a ridiculous experience, and thank you. That's all. Do you have any questions? Oh yeah, microphones. I want to know the joke question.
When are you going to write free? When are you going to write your free?
Never. I guess I could. Well, I need to. No, probably not. I learned a lot of things.
First, that's fantastic. I really enjoy your presentation. So I went to your GitHub page and it says, warning, this does not compile right now for anyone except me.
Yeah.
When will I get to compile it?
Probably never. I'm being serious though. So it compiles using a very particular version of Rust, probably a nightly build from like circa December 17th. And you also need to do some weird things with Rust core. Like you need to have a particular version and then also like have like monkey patches to it. If you were interested in compiling it, I could probably talk to you about it. I don't think that the code is fundamentally super interesting. Like the interesting thing to me is like what I learned. The code is kind of crappy. Other people have done much like more technically interesting work. I think if you want to learn about the code, it would probably be better to read my blog posts, which have like the concepts involved. But like the actual code, I don't recommend in any way. Yeah. But if you want to make it compile, like, please.
Hi. Now that you've descended into operating systems land, did you really like the whole? Did you like everything that you found out about it, or are you of the opinion now that this is fantastic that people have built this stuff? I want to go back up to a higher level so fast.
Both. Like it was super fun, and I kind of thought like for a little bit about trying to get a job doing it, because I was job hunting afterwards. I ended up getting a job doing like machine learning and data analysis, which is like much higher level. I got a lot of appreciation for what's involved, and I did think it was really fun. And it's something I would maybe consider doing like when I get bored of whatever I'm doing now. Yeah. Are there more questions?
Do you like Rust?
Oh, I don't know. Like, I like the people who do Rust a lot. Rust, so like it was really confusing. That wasn't like this is the worst. No. So it's really interesting. It changes every day, as far as I understand. So it was like really frustrating because of that. Because I'd be like, I wrote this code, and they'd be like, that was yesterday. Like, and like I thought I knew things, and then they were never true. So like it's hard for me to think about Rust partly because it's so unstable. So if you're not paying attention to it like day to day, and I was only doing that for 3 weeks, so now like all of my knowledge is like 3 months old, and I just imagine that like all of this code that I wrote, you're like, what language is that? Like, so like it's hard to like Rust, I guess, if you're not paying attention to it all the time. For me, yeah.
Which part of the standard library did you miss the most?
So I haven't written Rust with the standard library. Like not seriously. So this is like my only experience of Rust. Yeah. I don't know. What, is there anything else? I'm also happy to talk to you afterwards. Cool. Thank you.
All right.
All right. Hey, everybody. Let's settle down so Patrick can start.
All right. Hi. So I'm Patrick Walton, PC Walton on IRC. I work here at Mozilla on Rust and Servo. And today I'm going to talk about, this is just going to be a really quick overview of Servo parallel layouts. So for those who don't know, Servo is our web browser that we're writing in Rust. It is, well, it's a browser engine. It's not a browser itself. It's a research browser. It's not designed to be, it's not something that's a product, and it's designed for testing and experimenting with different approaches to render the web. And so it is almost entirely written in Rust. Well, it depends what you mean by almost entirely. So the layout, all of the rendering, all of the graphics, it's all written in Rust. All the CSS, the HTML parser is currently written in C, but that is, as we speak, being translated to Rust. Altogether, it's over 100,000 lines of Rust, quite a bit, and it's growing. We've been working on it for, I think, just over a year now. Well, no, more than a year, 2 years, really. But it really only started to pick up in earnest over the last year. And yeah, so at the end I'll give a demo, but I won't spoil it right now. And what I want to talk about today is some of the experimental stuff that we're doing.
You said it's 100,000 lines of code. For comparison, how big is Rust C and lib standard?
Last I checked, Rust C was like 80,000, but that was like 6 months ago or something. So it may be more now. And of course, that doesn't count lib standard, which is fairly big, lib syntax. The entire distribution's 200K, says person. So yeah, this is getting to be, kind of a real project. And so yeah, so what I'm looking at, so one of the things that we're doing in Servo is experimenting with how to use multi-core systems, and even we're doing some experimental work on GPUs, and I'm not going to talk about that today, but we're looking at how we can use multi-core systems to make the web rendering faster. And in particular, what we're not looking at is JavaScript right now. JavaScript performance has been a really big focus, and it's a really big focus of other teams, and we're just using the SpiderMonkey engine. What we're really focused on is CSS, the DOM, rendering, all that stuff, and because I personally think that's one of the biggest bottlenecks of the web in practice. There's a lot of I remember a colleague of mine actually, Luke Wagner actually did an experiment where he turned off the JIT and browsed for a week and didn't notice a difference. And so when it's actually, JavaScript performance has gotten a lot of attention because it's really easy to measure, and I'm not saying it's not important. It's extremely important for a lot of new things that people are doing. But when it comes to your day-to-day browsing experience, I really think that rendering is really king. So we've started to, and I think there's a lot of opportunity here because browsers were designed in an era of single-threaded, event loops that block everything. And at first that was great because the web was small and there wasn't a whole lot you needed to do. And then CSS2 happened, and then CSS3 happened, and then stuff that isn't even in CSS3 happened, and then suddenly browsers became like 6 million lines of code. And they're all on this single-threaded event loop blocking everything model. So in Servo, we thought, okay, well, one of the first things we're going to do is to split up everything into multiple tasks, multiple threads. So basically everything that we could possibly get away from the main event loop, we got away from. So basically nothing runs. Another way to say this is nothing runs on the JavaScript thread except your JavaScript, more or less. And everything else is done in a background thread. And then we thought, well, that's great. That's great for responsiveness. It means that when layout is hung, you can still browse the page. You can still re-render stuff. That's great. But what if we went further and said and it also means that we have iframes in a separate thread, and that's really great. But it means that your ads won't make the rest of your page slow. Your like buttons, your hundreds of like buttons on TechCrunch won't make the rest of the page slow. That's great. But what if we made layout? What if we took advantage of your cores that were in your system to make layout faster and just make the whole thing faster? And so one of the nice things about there's actually some research that's been going on in academia on exactly how to do this, exactly how to make CSS faster by using multiple cores. So we weren't sure how this would really work. We really started working on this, I'd say, about 6 months ago. Really, actually, this code is only a few months old. It was really in the past 3 months or so that we've actually started to really focus on parallelizing layout, and we've started to see some nice gains in real-world sites. This is a quad-core machine here. I often see 2 to 3x speedups. So I'm going to talk just briefly about what goes into that. I won't bore you with CSS algorithm, with like the nitty-gritty CSS algorithms. I have a blog post on some of those. Instead, I'd like to focus on kind of the general Rust, on the general thing that we use in Rust, and I would actually like to, which is right here on the screen, and I'd actually like to upstream this into the Rust standard library soon. So this is something, so what you're looking at here is something called the work queue. And a work queue and Rust, as you may know, when you do multi-threading, you have tasks. Tasks are great. They can communicate with message passing. They can do, they can block on I/O. So you can do, you can spawn like a task for your web. If you have like a web framework, you can spawn a task for each connection. They're pretty lightweight, and they can block on network requests and all that. And they're multiplexed into OS threads. But in some cases, the overhead of tasks is just too high. And the reason that the overhead of spawning tasks can be too high is that they have stacks and they can block. What that basically means is that when there are points in which tasks can stop execution, they can block. Like, for example, is waiting on a network request or sending a message to another task, waiting on that. In that case, you have to basically suspend what the task is doing and switch to another task. And because of that, you have to allocate space for the task stack. You have to allocate space for each task, for each task's stack manually before you start the task. And that is actually, and that overhead is very high for some cases. When you're doing parallel layout over a document, you may have 100,000 nodes that you're going to that you need to parallelize in 10 milliseconds. So if 100,000 10 milliseconds divided by 100,000, that gives you like 0.0001 milliseconds per DOM node. At that point, allocating a stack is so expensive that by the time you've done that, you could have already done all the computation needed for that node. So you need something much, much cheaper. And that's what this work queue is. The work queue is a super cheap way for you to enqueue units of work. And here's the unit of work. It's parameterized over really terribly named type parameters, quad and wud. Quad is for data that the work queue has, and wud is for the work unit data. And that's all you get. And you get a function. And that function has to execute. And it has to fully execute. It has to do everything. It has to do, a work unit is kind of like a task, except you are not allowed to do I/O, or at least receive on I/O. You're not allowed to send or receive messages. And you aren't allowed to access any data, really, other than the queue data or the work data. It's very restrictive. But it turns out that that's enough if you're going to have if you're going to parallelize over nodes. And the end result of this is that actually creating these things and then queuing these things is ridiculously cheap. It's like putting a couple of pointers into. It's basically like putting a couple of pointers atomically into a queue, and that's all you have to do.
Does Rust enforce those restrictions?
Yes, we enforce them. So the Rust language doesn't know anything about work queues, but we use the Rust type system to enforce that this is all safe. So what we actually do here is because because the work queue is so similar to the task scheduler, we actually use a lot of the guts of the task scheduler in the work queue. So you notice that we have this thing, this standard sync deck. That is actually the same thing that the scheduler uses, and that's this thing called a work stealing deck. And I won't quite get into that, but that is actually, it's the core of the scheduling algorithm is in Rust, actually lives in this library called standard sync deck. And all I did was take it and reuse it for something lighter weight. So this is where the fact that the Rust scheduler is written in Rust is really, really helpful, because I could just take little bits of it, and that I didn't want to use the whole thing. I just took little bits of it and then redid and then wrote my own scheduling algorithm. So basically, how you use this thing is if you're doing your own parallel data. For example, say you're writing a game and you might have 100,000 actors in your game. You might want them to all work in parallel. The work queue might be really nice for you. So what you do is you make one of these things. You tell it how many OS threads you want, and then you give it some user data that all of your work units can access, and it makes a work queue. And then what you can do is you can push onto the work queue. You can make a work unit, and then you can say run. And what run does is that it runs all of the units in the work queue, and then when they're all done, and it blocks until they're all done, and then returns to you. And then you can call shutdown to destroy the thing. And one important thing is that work units actually receive a worker proxy reference. And what a worker proxy reference is that it's an object where you can actually enqueue, work units themselves can actually push new units of work on. This is really useful in layout because you have, when you have a tree, you start out processing the parent, you start out processing a node, and then you push all of its children on as work units, and you kind of fan out the work that way. So yeah, this is basically so this is the core of the parallel layout algorithm in Servo. And now for a fun little demo. Hopefully this will work. I can show, this is my build from today. I can show Wikipedia rendering, off the screen. This is actually Servo rendering Wikipedia. You can see some, scroll around. Obviously there are some bugs, but it's basically correct. We're getting farther and farther, and yeah. So and this can all be rendered in parallel. And yeah. So that's basically the progress of Servo. We're making actually just a few days ago, the sidebar was, or actually just earlier today, the sidebar was all smashed together, and so we're making improving that every day. So yeah, are there any questions?
Document.write is not a function? That would be so nice.
Yeah, it would be. Brian?
Your work unit is an extern fun with user data.
Mm-hmm.
At what point is that going to be a closure?
Let's see, an extern fun with user data, it could be a closure. I haven't thought too much about that. I would have to think about what the bounds could be.
Right.
I think it probably
It seems
could
like we're
be.
not expressive enough for that yet, but to be a real API, that should be a closure.
Probably an unbox. I probably need the unbox closures first, because you want the data to be packed right next to the function.
Okay. Second question.
Mm-hmm.
I thought Rust had. Sorry, I'm going to play devil's advocate. I thought Rust had lightweight tasks. Why aren't you using tasks?
Well, because you can't be as lightweight. As long as the task can block, you're already that's already too much. And Rust tasks are really lightweight, and that's great. I mean, you can spawn them a lot faster than OS threads. And that makes them really nice for web servers. For web servers, you may want to, for example, spawn a new task for every incoming connection. That's totally what they're designed for. But in some cases, that's too much power. The ability to block and wait and suspend your state and then come back to do it come back to it later is like what makes it work for web servers. Like you can't implement a web server without having that. Well, you could, but it's really annoying. Like it's why Nginx is implemented that way, and it's really annoying. So Rust tasks are a really nice sweet spot between the raw performance and the convenience of being able to block. But sometimes When you have like 100,000 DOM nodes that you have to lay out in like 15 milliseconds, then they're just too expensive. And that's one of the really nice things. I think it really shows like one of the really nice things about Rust. You're not forced into the concurrency mechanism. You're not forced into any sort of concurrency mechanism. If it's not working for you, just take the guts of it, like I did there, and make your own, and it works.
So you said that you can enforce that the work units won't do any blocking I/O. Could you show how you did that again?
Oh, wait, I don't actually enforce that they don't do any blocking I/O. If they do, they'll starve other work units. Yeah. So don't do that. But we do enforce memory safety, though. Like, they can't go and do evil things like race on each other. And that's really important for layout because CSS is really, really complicated. And like, I think what Brendan and I said when this project started, like trying to do all of CSS without having in a model that has data races is like juggling chainsaws. Like, especially if it's not even memory safe. So like, I really think the only reason, like, it becomes so much more practical to implement CSS if the language yells at you whenever you tried to do something that you shouldn't have done.
Maybe this is a little off topic, but are you finding that the API that you need to expose for the DOM is making it harder to parallelize the layout?
The API for the DOM is not so bad because basically the DOM runs in a separate thread from layout. The tricky thing is that some parts of CSS are really hard to do in parallel, like floats. Not talking about floating point. I'm talking about like float left, float right. Those are really hard. And I go into more detail on my blog about this. But they are really, floats are really bad for parallelism. Clearing floats is really good. There are some other things that are really kind of weird, like absolute positioning in some cases. But one of the things we found is that most websites are actually pretty parallelizable. I've done some experiments in the Alexa top 50 and found that a lot of them most of them are parallelizable. There are some ones that aren't, like Fox News and let's see, Reddit. But but you should shame on them for. You should send them email saying that that they should stop using floats so much. Yeah, Fox is like the worst news site for parallelism. It's the main reason you shouldn't go to Fox News.
Hi. I was just wondering how its performance compares to like existing renderers at this point in time, and how it's trending, and what your feelings are for.
Yeah, so that's a really good question. So I've done a lot of benchmarking. As we go through, I do a lot of benchmarking against existing engines. It's very hard to say where we are. It's very hard to give one number to that because, like, some things are done, some things aren't. Some things are just like stub implemented. If you look at the parts that we've actually optimized, we're really good in many cases. Like the core layout. The core layout in most cases is faster than existing engines, even when you limit it to one core. And I don't know exactly what. And if you do multi-core, obviously it becomes faster still. And I don't know exactly why that is. Some of that may be just the Rust language doesn't like virtual methods as much. So we tend not to write virtual methods everywhere, which are usually slow. Existing engines in C++, you don't have to write virtual methods, but it's so, like, the language favors it so much that people use virtual methods a lot, which actually leads to performance issues. I think that's part of it. Another part of it is just, we have the benefit of hindsight, and so, when you write, Gecko was brought, kicking and screaming into the world of CSS2 and CSS3, and now we kind of go directly there, which is always nice. Some of it, but I shouldn't say too much about it because we also haven't implemented a lot of CSS, so you never know whether I don't want to sit up here and like quote numbers because they may be wrong when we go to implement more of CSS. But I do feel pretty good about it. Selector matching is also an area that we're pretty competitive in most cases against other browser engines. Selector matching also parallelizes very well. Anything else? Okay, well, if you have any more questions, feel free to find me afterwards, and thanks.
All right. So my name is Alex Creighton. Like Patrick, I work here on Mozilla on Rust, and I'm kind of working mostly on the runtime nowadays and kind of things related to the runtime. And today I'm going to talk to you about debugging in Rust. This is not related to kernel debugging. I'm sorry about that, but this is more user-land debugging, kind of like some tools that I've seen you can use, kind of what you can do. This is kind of just going to be a brief cyclone interview of lots of stuff you can do. So. Rust is a compiled language, which means that it's kind of hard. Sometimes it's a little difficult to do things at runtime when you have some state and you don't want to have to go through all the effort of recompiling the binary, and you kind of want to use it as is, but you still want to instrument it at runtime. And typically for things like C and C++, the best use case for this is GDB or LDV. So in this case, let's say we have a small program like this, where all we do is just run a really dumb factorial function, and we're just going to print out the factorial of it. So we can just compile the binary. And then it's as easy as just running it all in LDB. And we have this -G flag that I passed is our debug info flag. It's the same as GCC and Clang and such, but it basically says, emit some lots of debug information so I can get some nice, pretty output here, which you'll see. So the first thing we're going to do is we're going to break on the main function, and we're going to kind of inspect the state of the world as it is there. So when we run it, the first thing we hit is actually the C main function. You'll see up here that it broke on 2 locations. So we're just going to continue past that. And then here we are in our own main function, which if you look at the file itself, you'll see that the exact source, even the line numbers are all inline straight in right there. And we could even do things like print the value of X and realize, wait a minute, that statement hasn't actually run yet. So we'll run a few instructions, and then we can say, let's take a look at the value of X. So now X is 4. And we can do lots of fun stuff after this, such as we can say, let's set X to 10. And then X is now 10. We can print X, see that it's 10. And when we run the whole program, we just altered the runtime of the program to say 4 factorial. Instead of calculating what 4 factorial was, it calculates 10 factorial. And if we run it again, we can see that it actually runs and prints 4 factorial. So this is kind of just a whirlwind, what you can do, like what you would expect out of a debugger in C and C++. You can pretty much expect the same thing out of Rust now. Our debug info is really good today. It's getting even better every day. We have a contractor working on it right now, which is doing lots of good work on that. So some other stuff you can do with LDB, which is really nice, is let's say we have this a big function where we just kind of main calls something, which calls something else. And we just kind of have a stack trace, which we want to kind of look at. So we'll compile the program real quick. And let's say we want to break on the function foo, which is here at the top of the stack, where main is just calling bar and bar is calling foo. So we'll just break on foo. We'll run the function. We'll see that we're right there, sitting on the foo function. We can kind of just take a look at the backtrace. And the great thing about this is we have both the function names, so this is the binary that it comes from, the name of the function, and this is even saying the file that it was found in and the line that it was found on. So typically, if you don't have debug info, you'll still get nice backtraces and everything, but you won't quite get the file name and line number. But this is a great way to like freeze your program, kind of look where you are, and normally from stack traces I found you can actually debug a lot of things out of that. So that's kind of an example of how you can use LDB or GDB. GDB is pretty much the same way with different commands, but you could everything you would expect from that in C and C++, you can kind of get the same thing in Rust. So let's take a look at another one, which is a fun bug that I found a while ago, which was came up on the issue tracker. So we have this innocuous program where all it does is a bunch of times. Let's just walk around this directory, where walk directories just kind of recursively go through and give me paths, and we'll process it. And currently our process function is let's just drop it and not worry about it. So we run it, and it works just fine, and it actually exits. It takes a little bit to run. But we get some reports from people saying that it's actually leaking memory. So what we're going to do is we're going to use OS X has this native app called Instruments, And this is, I'm going to kind of show you how this is meant to work with Objective-C and C++, but it works almost exactly the same with Rust. So we're looking specifically for memory leaks. So we're just going to, I already configured it, how to find it and everything. So we're going to run this function. I'm going to type in my password. And we can see that this is a graph of allocations as they're going on. We can see really easily there's probably a memory leak somewhere in this program. So when we come down here, we can say like, oh, okay, looks like libuv is doing some UVFS work, which you probably can't read, but it basically means that we found a memory leak, but it's not in Rust at all. This is actually in Rust using C libraries. So we're not only debugging Rust right now, but we're actually debugging across the boundary of Rust and C, and we're actually debugging other code. So you can, this is when let's say we upstream the fix to libuv, and now it's all compiled, and once we've recompiled everything, we can take another look at the memory graph, and this time we can see it's a nice flat line where we're not spiking, and it turns out when this finishes, we don't actually have any leaks. So this is kind of an example of, this is a native program which has 0 alterations to run with Rust, and it just natively can figure out everything, and it can just help you find bugs, find memory leaks. OS X has other things like time profilers and lots of other fun tools in there, but Rust code and binaries kind of work seamlessly with all of these tools just because it's native code generated by LLVM. So let's take a look at another one which is added very recently actually. Oops. So if you take a look at this file, it looks pretty innocuous. It's kind of just an example of some Rust code. I pulled this off the issue tracker because it has some fun semantics when you try to compile it. It crashes. Now this isn't a very useful error message. It says I called option unwrap on a none value. Well, that could be anywhere in the code base. If you so there are 249 instances of unwrap. That could be any of them. Plus it could be on the standard library. So let's kind of an awesome thing you can do now is print out backtraces at runtime. So what I just did is I set an environment variable saying that I want you to print a backtrace when you fail. And now we can say we don't even have to use LDB, we don't even have to use GDB. We have native support now in the standard library to print backtraces on failure, well, on task failure. So here we can see that this unwrap function was probably called from this check match is useful specialized. I don't quite know what that is, but that's an excellent place to start. So this is generally available for all binaries. So if we take a look at this example right here, it's just a couple of stacks of functions which eventually call the fail function. And if we compile it, don't even need debug info, and we run it, it'll fail. But if we set the environment variable, we get a nice backtrace. And we can see that we have our main function, and our baz function, our bar function, and our foo function. Now, this doesn't quite stand up to optimizations. If you, the backtraces are all done at runtime with libunwind and or special things in Windows. So if you do the same thing with optimized code, it actually just fails right on the main function because everything was inline. So this is a great way to kind of see a general idea of backtraces at runtime, which is a lot easier than sometimes running in a debugger. But you're not necessarily guaranteed to have the best debug information in terms of inline things and programs like that. So let's take a look at this. So we have another bug in the Rust compiler, which looks pretty innocuous, but this looks like a trait inheriting from itself, which sounds like a Stack Overflow bug. And if you do it, you do indeed get a Stack Overflow. And this is just also showing, so if we want to debug this, backtraces are kind of tough to print on Stack Overflow because you have lots of things going on. But this is another case where you can just use LODB and figure it all out. It's a little bit more difficult though, so this is something, I just ran it in LODB and it just died. So let's take a look at the backtrace and see what we can see, but it turns out we don't see a whole lot. We see this Rust stack exhausted function right here, but that's not really helping us a whole lot. So this takes a little bit of knowledge, but if you know that there's a more stack function, which is this magical name, and you run it again, then you can actually see, I'm only going to print 10 frames because there's a lot. But we have a nice, we can diagnose this Stack Overflow with LODB just kind of like you would normally see. And you can probably pretty easily see that here we have this AST conv, AST path, and then up here we see probably the same thing. as we go farther down, you can probably quickly find the cycle and quickly debug problems like this. Not necessarily in the Rust compiler, but in kind of generic Rust code itself. So as the last thing, I want to show you that Valgrind also works really well for Rust code. So generally, Rust doesn't have many memory leaks because it has own memory, managed memory, and it's all automatically done for you. But a lot of times you're interfacing with a C library, and you're not necessarily certain if you're using the C library correctly. So let's take a look at this little test application I wrote. We have some library next to us, which just has an initialization function, and then you can print some stuff inside of it, and then later on you want to free any resources associated with that object. So, and this is just a small little demo thing, and the program itself looks like, let's initialize it. If it succeeded, then let's print it, and then let's free it. And if it didn't succeed, then we'll just print out that nothing actually happened. So if we compile this and then run the program, we can see initialization failed. Well, that's expected. It's probably pretty normal for C functions to fail occasionally, but we get some reports that this is actually leaking memory, and we're not really quite sure why. So we can actually just run Valgrind on it natively, and if you take a look at it, on OS X you get some weird false positives. Like this is stuff from Objective-C initialization. So we're just gonna suppress these errors. This is a special Valgrind thing, which you can say, like, don't print information about these errors. So here we see, we get a few warnings at the beginning, but that's about it. And the real important part is we've lost 4 bytes in one block. This means that we have a memory leak of 4 bytes in our program. And if you take a look at the Rust code, it doesn't actually look like there's a lot going on here. This is the only part where we're actually doing things. And maybe this initialization function is allocating memory, but it turns out that if you take a look at the C library, we see that the initialization function always mallocs memory. It has this nice little comment saying that you have to call free foo no matter what, whether initialization succeeds or fails. So this is an example of a bug which I've actually run into many times, which is basically you can, in writing safe C bindings, you often run into many bugs, and you might actually use the C library incorrectly. So we can come over here and modify this function, take this free statement, and put it at the end, just because it said that I should always run the free function. So we can recompile, we can run under Valgrind, and we see we have lost no memory. We ended up freeing all the memory. So this is kind of basically showing that Valgrind as a tool is not necessarily, like, the usefulness is kind of degraded from C because you get safety by default. But whenever you're interfacing with unsafe libraries or unsafe code, this is a fantastic tool still, and it works just perfectly with all Rust code because they're all just Rust binaries and everything. This is also great for finding data races if you have some unsafe sharing of data and you're kind of breaking the compiler as is. So that's all I have for today. Maybe more debug info later, but thank you for listening. Are there any questions?
I have a question. Go ahead. So earlier you had a stack frame where main calls foo and foo calls bar, and you showed us the sort of DAC backtrace. And there was an extra frame between foo and bar.
I found that as I was writing this, actually. I think it was, is this, yes. Oh, maybe it's not that one. But yes, I'm actually not entirely certain why that is. We use libunwind to do the unwinding, which kind of in turn uses dwarf info, and that's something that I think I'll have to look into to try and fix because I'm not entirely certain why that's happening.
Do you do anything special for closures? Can you repeat the question? The mics are still very quiet.
Sure. So the question was whether we do anything special for closures in terms of symbols or like printing out the backtraces.
Both.
Yeah. So we like every closure is essentially just a function pointer and a data pointer, and the data pointer is kind of automatically managed for you, like it's automatically generated at compile time. So the function pointer actually does have a symbol associated with it, and it's a descriptive symbol. Let's see. I'll show you. So this is an example of a closure symbol, which needs a little bit of improvement right now. But what that should look like is RT : task : blah 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 : closure. So they don't have fantastic names. This is definitely a place where we can improve. And like this actually landed just this morning, so it's quite new. But we control this demangling. So the symbols actually look like this in the object file. They have this ZN and these numbers inside of them and this E's at the end. So we're the ones that control how we translate that to a name. So we can definitely add some nice sugar to it. The general idea though is take the outer function, what it's in, and like that symbol, and just append : closure, and then some sort of numbers on the side to disambiguate them. Yes. The mystery bug. Oh, I think I don't actually know. That was one which I just pulled off the bug tracker and ran. But it looks like a serious bug. Yes.
Any thoughts about how to debug, say, Patrick's parallel CSS rendering?
So the question was whether we have any thoughts about debugging Patrick's parallel CSS rendering, and the answer is I have no idea. Although I've heard that if you have bugs, it's probably not that bad, because if your frame is about 2 pixels off, no one's going to notice.
When you were doing the Valorant demonstration, you have passed in -- leak -- child equals foo, and I think that would be the backtrace.
It would. That was actually something I wanted to show. That is a good point. So the point, I guess, was if I run with leak check equals full on Valgrind, it'll actually give me the backtrace of where the leak came from, and then I ran it with the correct version actually, so it didn't help. So this one was the buggy version, and you can see that the leak actually originated from this init foo function, which was exactly where it was supposed to come from, which is where init mount memory and then didn't free it, or then I forgot to free it. All right, thanks so much.
All right, thanks everybody for a great talk. This was really fun. So for anyone who wants to talk about the Dockathon that's happening on Sunday, if you want to just meet up here and we can start figuring out what we want to do on Sunday. But for the rest of you, feel free to hang out for a little bit and mingle, and thanks for coming. Have a good night.